Hey, Jonathan. Good job. I just fed you. Now you grumpy. Good job.
Hey, Dr. Tran, how's it going?
Good. How are you?
I'm doing good.
All right. It's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
We're good. We're good. How are you?
Doing
Good.
well.
Good to hear it. Yeah. So it's Thursday of week 7. So we're almost reaching the midpoint of the semester. If not, we already reach it. So we have a couple more weeks of class after this, and then we hit spring break. Okay. So that's, I know, probably I think it's exciting news for all of us, right? But we have a bit to go before that. Okay. And so the plan for today is that we're going to finish up, or at least make really good progress on lecture notes 07, which is the finite element forms. Okay. And so you'll actually see, this is kind of the payoff for the last couple of weeks of investment of doing a lot of math. And so you'll actually see, how we can take the weak form, how we can take the shape functions, and how we can bring all those together to actually form a finite element problem. Okay. So today, we'll see how to form the element stiffness matrix for these kinds of problems. And then we'll do an example to kind of show you, how this all kind of fits together. Okay. All right. And then next week we have a busy week. So we have a lot going on next week. So Tuesday of next week, we have our next ANSYS activity. And so on Tuesday, we're going to be doing an ANSYS activity on a signpost. Right? And so we're going to be building, just like the previous activity, we're going to be building up on our, ANSYS skills that we've developed so far. But on Tuesday, we're going to add something new to the mix, which is assemblies. Right? And so technically, ANSYS activity 2 also, I gave you an assembly there, but we suppressed everything except for one part. And so on Tuesday, what you'll see is, how do you actually work with an assembly, how you can assign different materials to different parts, and probably most importantly, how do you define the connections in between the different parts of an assembly? Okay. So I think that's probably going to be the most important thing to take away from Tuesday is, when you have multiple parts that you maybe created in assembly and in SolidWorks, you have to define how those parts are going to interact within the finite element simulation. Okay. All right, so that's going to be the plan for Tuesday, and then Thursday, of course, is our midterm exam. And so yesterday afternoon, I posted up the review video for the midterm. Okay, so definitely check that out as you're preparing for the exam. In particular, what I showed in that in that review video are basically examples of problems that I'm going to ask you to do. Okay, and so I think I redid a couple of the homework problems, but I did it in the style of what I would expect you to do on the exam. Right? And so hopefully what you'll see is that it's a lot less calculations, and it's a lot more stable, I would say. So hopefully that eases things up for you guys. So definitely check that out. When you start studying for the exam, either this weekend or next week, and then just let me know if you have any questions on it. Okay. All right. So are there any questions that I can answer before we get started for today? Okay. Oh, and there is stuff due. So I think homework 2 on the beam stuff is due tomorrow night, and so definitely make sure you get that in. And I know there's kind of been a lot, and so I kind of wanted to avoid the situation of two things going on at the same time. But remember, the homework assignments in this class, they're graded for completion, and so I would say, as long as you're giving a good effort on the homeworks, then that's enough for me to give you full credit for it. But definitely spend your time wisely, because I know you guys have a lot of other stuff going on with other classes and other other responsibilities too. So I know these problems tend to be really time consuming. So definitely give it your best effort, and then if you're not getting it, then I wouldn't spend too much more time on it, because it's I know you guys have a lot of other really important things to do as well. Okay. And then once the solutions come out, so I plan on grading those probably sometime either Saturday or Sunday. And as soon as I finish grading those, I'll put the solutions up, and so you'll have the solutions for those homeworks before next week begins, so you can use that to help you study as well. Okay. All right, and so let's go ahead and continue where we left off on Tuesday. Right, and what we were looking at was what I like to call finite element forms. So this is kind of like part 4 of this long series that we've been doing of taking just a generic differential equation and then turning it into a finite element problem. Okay. And the reason we're doing this is to kind of give you an idea of what are the capabilities underneath ANSYS, right? And so ANSYS, when we've seen that we've opened it up, there's a lot of capabilities inside ANSYS, right? And it might seem, I think at first, when you look at that, it's like, wow, they can solve structural problems, they can solve heat, they can solve electromagnetism, they can solve fluids, right? It seems like all things that are very unrelated to each other. But they are kind of all related, because they're all related in the fact that they're all solved with differential equations. They're different differential equations, of course, but we can apply the exact same method to them to solve them, right? And so ANSYS based, it seems like ANSYS has put together this amazing software, and it's an amazing software, but a lot of it's kind of built on top of each other. So they basically just use the same methods in the code to just solve different equations. All right, and the driving force behind this, or the way that we do this, is our weak form of our boundary value problem. Okay. And so I'm just going to write one term of the weak form here, because that's what we're going to spend most of the time on today. It's going to form our element stiffness matrix as well, right? So let me focus on just the term with the derivatives. Okay. And so we have the integral from 0 to L. Okay. And then we have dw dx times EA times du dx, and then dx, right? And so this is for our 1D elasticity equation because we're solving for u here. Okay. And remember, w is our weighting function, so it's almost like our little brother that's our helper. That in the end, we don't really care too much about, but what he does is that it helps us get the order of the derivatives down. Okay, so instead of solving a second order differential equation, what we have are these two first order derivatives. All right, and so before we talk about the finite element form, what I'm going to do is I'm going to break up this integral into a bunch of smaller integrals. And so, what I'm going to do is, for a 1D domain, normally we have, a domain that looks like this, where on the left-hand side of the domain, we have x is equal to 0. And on the right-hand side, we have x is equal to L, right? And that's what we're integrating on. And so we're integrating our solution over our entire domain. And so if you remember, when we do finite element problems, a big part of it is breaking up this domain or discretizing it into a bunch of elements, right? And so that's what we do in the meshing step. Okay, so let me do this. Instead of working with this big line, let me break it up into all of these small elements. And then I'll label all the nodes, x1, x2, x3, x4, x5, x6. Okay? And so these denote basically the nodes in your finite element mesh that you would produce in a software. Okay? And so instead of, what the finite element method says is that instead of solving one integral where you integrate over the entire domain, let's break this up over, each of the different elements. Okay? So let's integrate instead from x1, x2 of dw dx, EA du dx, dx. Okay. And so the integrand is the same, but what I've done is I've just changed the bounds of the integration, right? And so instead of going from 0 to L, I'm only integrating over that first element. Okay. And so if we call this element A right here, okay, this integral right here is an integral over element A. And then next, what we can do is we can integrate over the next element, right? And so if we call this next element B, right? What we can do is we can, write this integral for that one. Right? So we can have integral from x2, x3 of dw dx, e times a du dx, dx, right? And so this here is the integral over element B. And so we're making use of the fact that, when you have an integral over a long domain, you can break it up into separate integrals, over each of the subdomains, okay? Right, and so this here is for element B. Okay. And then so on and so forth, right? And so we can have basically the exact same integral, over all the different domains of the problem, okay? So if we have element C, then we'd have an integral for element C. Element D, we have an integral for element D, and then element E, we have one for E. So however many elements that you have in the problem, basically that's how many integrals that you're going to solve. Okay. And this kind of approach it lends itself really well to a computer algorithm because, because the integrand for all of these elements are basically the same, right? And so basically we have the same thing on the interior, dw dx times e times a times du dx. Since all of those things are the same, we can kind of, computerize this, or basically, write instructions for this to do on a computer, and then just tell the computer to just do this over and over and over again, okay? And that's kind of the basis of a finite element method, right? And so, what we're going to do next is we're going to focus on the solution for just one of the elements, right? And so, let's say that we focus on just element A for this case, and then from this, we'll be able to derive the element stiffness matrix. Okay. All right. Any questions on this? So let's work on the element stiffness matrix. And so, we're already familiar with element stiffness matrices because, we've worked with them a bunch with our trusses and beams. But here, we're going to come at it at a much more general way. Okay. And so we're going from basically, this, instead of leveraging, the structural mechanics of a truss or a beam, we're coming at this kind of, directly just from the mathematical expression. Okay, so let me write out the integral for one element. Okay. Right. And so we have integral from x1 to x2 of dw dx times EA times du dx dx. Right. And then also on the right hand side, we have the integral over the forcing term, right? Or the body force term, as we think we called it. And so we have integral from x1 to x2 of w of x times b of x times dx. Okay. And notice, the bounds for these integrations are just, x1 to x2. Okay. All right. And so at this point, what we're going to do is, we're going to plug in our interpolation functions for w and u. Because if you remember from last time, we what we did was we assumed that our u, or we assumed that our w was a linear function, and then what we did was we derived an expression with the shape functions. Okay. All right. So let's go ahead and do that. And so if we assume that they're linear functions, and so we'll assume linear, what we get is the following following equations, right? And so w of x is going to be w1 times n1 of x, and then plus w2 n2 of x. Okay. Where w1 and w2 here are the values for w at the nodes. Right? Eventually, what you'll see is we're not going to care, what w1 and w2 are, but we kind of just need them as tools for now. Okay. And then we'll make the same approximation for u of x. Okay. So u of x here is going to be u1 n1 of x plus u2 n2 of x. Okay. And u1 and u2 here, this is what we're interested in, right? Because u1 and u2, these are the solutions to our equation at the nodes in our grid. Okay. And then just like we did before, let me put these guys into vector forms. And so for w of x, we're going to say that this is w1, w2 row vector times n1 of x, n2 of x. Right? And then u of x will be n1 of x, n2 of x times u1, u2. Okay. And so, if you perform kind of the vector-vector multiplication for these, then you end up with the exact mathematical expression that you have above. Right? But the reason we do this is so that, in the end, we'll be able to compute a stiffness matrix from it. And what you'll see is that, the convention for W and U here is reversed, right? And so for W, we have W1, W2 in the row vector. And for U, we have N1, N2 in the row vector. Right? In the end, you end up multiplying them and end up getting the same thing. But the reason we do this is to help us basically form a stiffness matrix. Okay? Okay. And so what we'll be able to do is basically plug these into our weak form expression above, and then use that to get a system of equations. Okay. All right. Any questions on this? Okay. All right. And so that's the that's the W and U functions by themselves, but we also need to take their derivatives in order to actually plug it in. Right? And so let's find derivatives of U of X and W of X. Okay. And so if you remember from Tuesday, when we take the derivatives of these, the derivatives just end up being on the shape function terms. Right? Right? So we take dw dx, we get w1 dn1 dx plus w2 dn2 dx, right? Because w1, w2, we assume that those are just constants, and so we're not going to take derivatives of them. Okay. And then we're going to put this in vector form, and so this is going to be w1 w2 times dn1 dx dn2 dx. Okay. And then same thing for du dx. And so du dx, we're going to just take derivatives of the shape functions. Okay. And then we'll also put this in vector form. And so this is dn1 dx dn2 dx times u1 u2. Okay. All right. And so now we can take these and plug these in. Okay. And so in particular, let me focus on just the term with the derivatives for now. Okay. And so our weak form expression, remember, was integral from x1 to x2 of dw dx times e times a times du dx dx, right? And so let's take the vector forms of these expressions and then plug them in. Okay. First, let me start out by taking actually no, we'll leave those in there. Okay, so we have integral from x1 to x2. First, we have a dw dx, and so we have w1 w2 dn1 dx dn2 dx, right, times ea, right, times row vector dn1 dx dn2 dx times u1 u2 dx. Right. Okay. And then from here, what we can do is we can simplify this by factoring out some of the constants. Okay. And the only constants that we have are the coefficients that come from w and u, right? And so this right here is a constant. And also this right here is a constant, okay? And then once we factor those out, we'll be able to get an expression for our 2 by 2 element stiffness matrix. All right, any questions on this so far? Okay. All right, and so if we factor those out, what we get is W1, W2, integral from x1, x2. Okay. I'm going to go ahead and perform the matrix or the vector multiplication. And so what we end up with is a 2 by 2 matrix, because what we have here is this matrix, or this vector right here of dn1 dx and dn2 dx. This is a 2 by 1 matrix. And then this vector right here is a 1 by 2. And so if you perform multiplication, you end up with a 2 by 2 matrix. All right, and so the 2 by 2 matrix is basically this. We have dn1 dx, dn1 dx, okay, and then we have dn1 dx, dn2 dx, and we have dn2 dx, dn1 dx, and then dn2 dx squared. Right. And so there's our 2 by 2 matrix, and then we're going to multiply by EA dx. And then on the outside, we have U times U1, U2 vector. Okay. And so what I've boxed here, kind of in the middle of this expression, this integral of this 2 by 2, this right here is our element stiffness matrix for a 1D problem with linear shape functions. And then from here, all we have to do is plug in for, dn1, all the shape function derivatives, and then we can evaluate this integral. Okay. So I know it looks pretty intimidating here, but in actuality, this is actually not that bad to evaluate. So actually, I would argue that this is a little bit easier to evaluate than all the truss and beam stuff that we've done up to this point, because a lot of the terms in here just end up being constants. And so if you're just integrating a constant, that's usually not too bad, not too bad to do. Okay. All right. And so that's the left-hand side of our equation, which is our derivative term, but we also still have the right-hand side, which was our our body force term. Okay. Okay. And so our body force term, this one's not nearly as bad. And so we're going to have integral from x1 to x2 of w of x, b of x, dx. And so we're going to plug in for w of x. Okay. And so we plug in for w of x, what we get is integral from x1 to x2 of w1, w2 times n1, n2. These are just the regular shape functions, because these are just, this is just w of x, not dw dx. Okay. Times b of x dx. Okay. And so just like we did for the stiffness matrix, since this w1, w2 here are constants, we can go ahead and factor them out of the integral. Okay. And so we have w1, w2 times integral from x1 to x2 of n1, n2, b of x dx. All right. And so that's, those are the two big integral expressions that we have. Okay. All right. Any questions on this so far? Okay. All right. And so, so that's our element stiffness matrix, and that's our body forcing term. And so you can see already we have a little bit of a difference from our truss and beam equations, because with that body force term there, we're able to now implement things like the effects of gravity or the effects of electromagnetic fields or of thermal generation. So that part's new. But let's take a look at actually one more term in our weak form before we kind of put it all together, and that was our natural boundary term, or our Neumann boundary term. Okay. And so our Neumann boundary term looked like the following, right? And so we had W times E times A times du dx. Okay, and we're evaluating this at the Neumann boundary. Okay. Let me make one substitution in here. And so, usually our Neumann boundary is given by, in terms of an applied stress. Okay, so this would be like, an applied load or an applied pressure. Okay. And so we know that the T bar here is going to be equal to E times du dx. Okay. And so let me plug that in for here. And then, what we end up with is W times A times T bar, which is what? Okay. And so just like we did before, we're going to plug in for W here. Okay. And the key here is, this term right here, and the reason I kind of saved this for last is that this term is only going to be evaluated wherever at the locations where we apply a load. And so for most of our elements, we're not going to consider this term because most of the elements are not going to be on the boundaries. And so for 1D problems, we're only going to apply this maybe to just one node in the system. Okay. All right. And so we plug in for W. What we get is W1, W2 times N1, N2 times A times T bar. Okay. And this is only evaluated at the place of loads. Okay. All right. And so now that we've had all of this together, we can kind of put it together with all of our other expressions that we have here. Okay. Because remember, our weak form was comprised of all three of these terms. So we had two integrals and also one boundary term, which came about as a result of the integration by parts. Okay, and so let's go ahead and put this all together on the next page. And then once you see it all, once we put it all together, then you'll see that we really don't care about what W is, and it's all those W terms are just going to cancel out from here. Okay. All right. Any questions on this? Okay, and so putting it all together, we have W1, W2 times integral from x1 to x2. And then we have our 2 by 2 element stiffness matrix. And so we have dn1 dx, dn1 dx, dn1 dx, dn2 dx, dn1 dx, dn2 dx, dn2 dx, dn2 dx, okay, times e times a dx times u1 u2, right? And so that was our element stiffness term, okay? Then we also have our body forcing term. So we have w1, w2 times integral from x1, x2 of n1, n2 times b of x dx, okay, plus our boundary term. So boundary term is w1, w2 times n1, n2 a t bar evaluated only at x is equal to x h, okay, which is the Neumann boundary. Okay, so it's it's a lot here, but a lot of it's going to cancel because if you see in every single one of these expressions here, we have a w1, w2, right? And that's that came from our weighting function. And so what we can do from here is just to cancel out all those guys, and we end up with a system, a system of equations. All right. And so just to kind of simplify this and to put it in a form that, that probably we're more familiar with, I'm going to take this, this integral here I've circled in orange, and I'll call it KE, and KE stands for the element stiffness matrix, okay? And then everything that I'm circling in purple right here, I'm going to call this FE. And so this FE here is going to be the element forcing vector, okay? Actually, I'm going to drop the E's for a second. All right. And so after we cancel out the W's and after we cancel out, and we group all these terms, what we get is an expression for our linear system that should hopefully look familiar, right? And so we have K, which is our element stiffness matrix, times U, which is our, forcing vector, which is our solution vector that we want to solve for, okay? And then we have F, which is our, element forcing vector, okay? And so this here is our stiffness matrix. Okay. This U here is the solution vector. Okay. And this F right here, which is, where, all the body forcing terms and all of the, all the loads, this is our forcing vector. And so it took a while, but you can see here that we've arrived at a linear system, that we can use to solve for for finite element solutions. Okay. The only thing I ask is that you just don't read this backwards when you're talking about this with your friends. Okay. All right. So any questions on this before we do an example?
That last term, evaluated at what? X equals what?
That's x is equal to xh, and so that's the Neumann. That's basically where our loads are going to be. So you'll see in the next example that usually you only have one location where you have a load being applied, and then you're only going to evaluate this term at that load. So for most other places, we're just going to ignore this. Yeah. So I call it h because h is a letter we use for the loads. Yeah. Okay. All right, so let's do an example just so you can see how all this kind of fits together. Right? So because we've done just a lot of really dry math over the last couple of weeks, so I think this example will hopefully help illustrate how all this comes together. Okay, and so here let's say that we have a bar with an expanding area. right? And so we have a bar that looks like this. And then let's say that the area is slightly getting bigger, just like that. Okay. Okay. And so at the left side of this bar, we have it's attached to a wall. And so over here, we can say we have a fixed support. Okay. And then on the right-hand side, we're going to have a compressive load. Okay. And so let's say that on the right-hand side, we have a compressive load of -5 pascals. In addition to that, there's going to be a constant body force all throughout, and so maybe we'll assume that there's a magnet on the right side of this that's pulling the bar out. Okay. And we'll say that this body force term is constant. So this B of x is going to be 2 newtons per meter. Okay. All right. And so what we want to do is we want to solve for the displacements in this bar using a 2-element system. And so our mesh looks something like this, right? And so we can have a bar that looks like this. Okay. And then we're going to put one node right there. Okay. And so we'll call this U1, U2, U3. Okay. And so that's ultimately what we're going to be solving for here. Right. Right. And so we'll call this, we'll say the x coordinate for the first node here is going to be 0. The x coordinate for the second node is going to be 5 meters. And we'll say x3 here is 20 meters. Okay. So it's a pretty long bar. And we'll call this, I'm going to use A in a bit. So actually, let's call this element 1. And we'll call this element 2 right here. Okay. All right. And since the bar is expanding, then our area is increasing as a function of x. And so let's say that our area function A of x is equal to 1 plus x squared divided by 400. Okay. And so one way you can read this is that, we're starting out with a cross-sectional area of 1 meter square on the left-hand side. And then by the time we reach the right side of the bar with x is equal to 20, we end up doubling our area. Okay. And then we'll also say that this bar is made of a uniform material. And so we'll say that it has a Young's modulus of 5,000 pascals. Okay. And so, from here, we're going to find the, finite element solution to this problem. Okay. All right. And so at this point, we're very familiar with finite element problems. And so even though, we're working under a new method here, or a new, way to get the stiffness matrix, our method for solving these problems is still going to be the same. Okay. And so just like we did with trusses and beams, our first step is going to find the element stiffness matrices. Okay. And in here we have 2 of them, right? And so we're going to do it for element 1 and also for element 2. Okay. All right. And so element 1, element 1 looks like this. Okay. And so element 1 on the left-hand side, we have x1 is equal to 0 and x2 is equal to 5. Okay. And so the total length of our element here is 5. Right? And so when we go to evaluate our element stiffness matrix, you can see here in the orange, we're basically going to integrate this guy from 0 to 5. Okay. And so I'm not going to write this whole thing down again because it's going to simplify quite a bit in a second. Okay. All right. So when you're solving these 1D problems, the first step that you should do is to compute the shape function derivatives, because this is this is going to save you a lot of work. It's going to save you a lot of work and a lot of writing in the notebook. And so our shape function derivatives are going to be dn1 dx and dn2 dx. And luckily for us, because we assume our shape functions are linear, these derivatives are just going to be constant functions, okay? All right, and so dn1 dx here is just going to be 1 divided by x1 minus x2, okay? And so I think we showed this, somewhat early on in the lecture on Tuesday. But if you look back in the notes, you'll see that this is the case, right? And so to find this derivative, all we have to do is just take the difference between the coordinate for x1 and the coordinate for x2. And so what we get from this is 1 over 0 minus 5. And so this is equal to 1 minus 1 over 5. And then dn2 dx is just going to be the opposite of that. And so that's going to be 1 over x2 minus x1. And so this is just going to be 1 over 5. All right. And so now what we can do is we can plug this into our expression and then, start working on getting the element stiffness matrix. Okay. All right. Any questions on this so far? Okay. All right. And so let's start plugging this in, plugging everything that we know into the element stiffness matrix. Because we know that our element stiffness matrix here is going to be integral from x1 to x2 of dn1 dx, dn1 dx, dn1 dx, dn2 dx, dn1 dx, dn2 dx, dn2 dx, dn2 dx, times e times a dx. Okay. And so knowing that, dn1 dx is just minus 1 over 5, and then dn2 dx is just 1 over 5, when we plug all those in, and knowing that all these guys are constants, we can just factor that out of the integral. Right? And so factoring that out, what we get is 1 over 25, minus 1 over 25, minus 1 over 25, 1 over 25. Okay. And we're going to integrate from 0 to 5 times E. E we know is 5,000 pascals. Okay. So that's E. And for A, we're going to plug in our area function, which is 1 plus x squared over 400 dx. Okay. All right. And so from here, all you have to do is just evaluate the integral and then just multiply it out. Okay. And what you get is, for the first element stiffness matrix, you basically perform all that arithmetic and all that integration. You get 1, 2, 1, 0, 2, 0, 8, 3, minus 1, 0, 2, 0, 8, 3, minus 1, 0, 2, 0, 8, 3, and 1, 0, 2, 0, 8, 3. And so that's our first element stiffness matrix. So this is basically just perform calculations. Right. And so we have that for that. Okay. All right, any questions on this?
Yeah, I had a question, Professor.
Sure.
So for the computing the shape function derivatives,
Yeah.
just assume that it's a linear solution.
Yes. Yeah. So that was kind of a big assumption that we made, and we kind of stuck with that assumption all throughout here. So, usually for these problems, I'll let you assume that it's a linear function because we'll talk about it a little bit probably probably in a couple weeks. But once you start getting to quadratic functions, it makes this whole thing even more of a mess. And so it's really complicated with quadratic ones. So and so you can basically for anything that I ask you to do, you can assume that it's a linear function.
Okay, thank you.
Mm-hmm. Okay. All right, so that's our element stiffness matrix. And then now we're going to do something new. And so we didn't do these for the truss and beam problems just because, for those, it was kind of more convenient to put those at the end, to do this at the end. But now that we have this body forcing term, we have to evaluate what's called our element forcing vectors.
Hey, Professor.
Yep, what's up?
And we still have to do the same thing for K2?
Yes, you have to do the same thing for K2. So we'll do that after we do everything out for K1. Yeah, so we're still on element 1 right now. Okay, and so our element forcing vector was this term right here. So we'll call this FE1. This was integral from x1 to x2 of n1, n2, b of x dx. Okay. And then from here, we're just going to go ahead and plug in for all of these guys. Okay, so plug in for n1, n2, and b of x. Okay. And so if we do all that, we get the following. So n1, when you plug in for n1 and n2, they all have a factor of 1 over x1 minus x2. Okay, and so we're going to factor that out of the integral. And then we have integral from x1 to x2 of n1, which is x minus x2, and then n2, which is x1 minus x. Right? And then our b of x here was just 2. And then we're going to integrate by dx. Okay. Okay. And so now we can plug in for x1 and x2. And so what we get from this is a minus. So x1 is 0 and x2 is 5. And so we have a minus 2 over 5 out in front. Integral from 0 to 5 of x minus 5, and x 0 minus x. So we just have minus x here. Okay, dx. And if we perform this integration, right, what we get is just 5, 5. Okay. All right. And so now that we have, our K1, and also our F1 here, we can use this to form our elemental system here. Okay. And so for element 1, okay, we have the following. And so we have first our matrix, so 1020.83 minus 1020.83 minus 1020.83, 1020.83. Okay. We need to make note on which nodes that it works on, right? And so this is just like in our truss problems. And you can see that element 1 here works on U1 and U2. Okay. And so we're going to multiply this by U1, U2. And then we have our element forcing vector, just like that. Okay. And so this is the system for element 1, and we're going to take the system later on and assemble it into the global system. But for now, we're just going to kind of leave it like this. Okay. And if you notice, when we were computing the element forcing vector, we didn't do anything with the load yet, right? And so remember, we had a load of -5 pascals that's being applied on the right-hand side. But since we were working on element 1, element 1 is, just comprised of this part right here. Okay? But the load isn't being applied on element 1. And so the load is actually being applied here on element 2. And so once we kind of repeat this procedure for element 2, you'll see where the load comes in for that. All right, any questions on this so far? Okay. All right, so let's do the same thing for element 2. And so for element 2, we're going to do the element stiffness matrix and also the element forcing vector. Okay. And so first thing that we'll compute here is we'll compute the shape function derivatives. Okay. And so element 2 looks like this. And so the left coordinate here is 5, and then the right coordinate here is 20. Okay. And so I know element 2 here works on nodes 2 and 3, but just for the sake of notation, I'm going to just call it x1 and x2. And so x1, in these systems refer to the left node, and x2 refers to the right node. Okay. So our shape function derivatives. Okay. So we have dn1 dx is equal to 1 over x1 minus x2. And this is equal to 1 minus 1 over 15. Okay. And then we have dn2 dx, which is just the opposite of that. And so we have 1 over x2 minus x1. And that's going to be 1 over 15. Okay. All right. And so now that we have the shape function derivatives, we can go ahead and plug this in for our element stiffness matrix. Okay. And so, I'm just going to go ahead and skip, a decent amount of the steps, but, a lot of them are the same as before. But remember, a lot of the terms in our element stiffness matrix involve, taking this multiplied by this, and putting it in 2x2 format. Okay. All right. So first thing I'm going to note is that, remember, our Young's modulus here is 5,000. And then the 2x2 part where, we multiply all the shape function derivatives, I'm just going to basically put in the terms here. And so we're going to have, minus 1 over 15 times minus 1 over 15. And so that's going to give us minus 1 over 225, or positive 1 over 225, I'm sorry. And then minus 1 over 225, minus 1 over 225, and then 1 over 225. Okay. And then we're going to integrate from 5 to 20, because that's the left side of the domain and the right side. And then our area function is still 1 plus x squared over 400 dx. Okay. And so if we perform this integral and then multiply through, we end up with the following. Okay. We end up with K2 is equal to 479.17 minus 479.17 minus 479.17, and then 479.17. Okay. And so that's our second element stiffness matrix. And we know what to do with this at this point. So now, once we get to assembly, we can kind of put this together with our old one. Okay. All right, any questions on this so far? Okay. All right, so that's the element stiffness matrix for element 2. And so now let's do the element forcing vector. Right. And so the element forcing vector, we're going to start with our body force term. And so this is the same as, element 1. And so our body force term, we're going to integral from 5 to 20, because that's x1 and x2, times n1, n2, times b of x, dx. We plug in for, n1, n2, and b of x, we get minus 2 over 15, integral from 5 to 20, times x minus 20, and then 5 minus x, dx. Okay. And so if we perform this integration, what we get is just a vector of 15 and 15. Okay. Right. And so that's the element forcing vector for element 2. Okay. But that's just the body force term, because remember, element 2 here also is carrying the load. Okay. And in fact, the location for this load is going to be x is equal to 20. Okay. And so what we need to do is we need to, evaluate that extra term for the Neumann boundary load. Okay. And so what we have for that is n1, n2 times a times t bar, and we're going to evaluate this at x is equal to 20. Okay. And so same thing we did before, and so we're going to plug in for x1 and x2 here. Okay. And so we're going to have a minus 1 over 15 times x minus 20, and then 5 minus x. Okay. We need to plug in for a, and so a here is 1 plus x squared over 400. And then we're going to multiply by t bar, where t bar here is minus 5. Okay. Right. So let me just kind of label this. This right here is our applied load. Okay. Right. So remember, minus 5 was the applied load that we put onto the system, and then everything else, is just our shape functions and our, and our area function. Okay. All right. And so everywhere that we see x here, we're going to plug in 20. And so what that, will do is that on top here, we're going to have 20 minus 20. And so this is going to be 0 up here. Okay. On the bottom here, we're going to have a minus 15. And so you can see that's going to cancel out with the minus 15 out in front right there. Okay. And if we plug in 20 right here, you can see what we get is 2. Okay. And so in the end, what we have is 0 and 1 multiplied by 2 multiplied by minus 5. Okay. And then what we get from this is 0 and minus 10. And so this is an additional load that we're going to input onto, onto this element. Okay. And so the total element forcing vector is just going to be the sum of these two guys. Okay. Any questions on this before I write out the full element system here for element 2? Okay. All right, and so for element 2, we get the following. So we get 479.17 minus 479.17 minus 479.17, 479.17. Then we're going to multiply this by U2, U3. Okay. And then on the right here, we're going to have the sum of our two forcing vectors. And so we have one that comes from the body force term and then another that comes from the Neumann condition, right? And so we're going to have 15 plus 0 and then 15 minus 10. And so what that gives us is 15 up top and then 5 on the bottom. Okay. All right. And so now what we have is the full elemental systems for both elements 1 and element 2. And so now at this point, we know what to do because, we've done this so many times before, is we need to assemble, and then we also need to apply our constraints. Okay. But first, let's work on assembly. So we draw kind of a big system here. We're going to add a little bit to our assembly here because we're also going to assemble the right-hand side as well. Right? So before, we focused just on the assembly on just the left-hand side matrix, but now we're going to assemble on the right side as well. All right, so let's start with element A. Okay, so element A, I'm going to put in this kind of a magenta color. Okay. Right, and so we're going to fill in all the values for element A into the places that I boxed in red. Okay, so we're going to have 1020.83 minus 1020.83 minus 1020.83 and then 1020.83. Okay. And on the right-hand side, we're going to put in our two values for the loads. And so that's going to be 5 and 5. Okay. Okay. And so now we're going to do element B. And then element B, we're going to do on this box right here. Okay. And so we have a little bit of overlap on the central node here. And so we're going to have 1020.83 plus what we have here, so 479.17, and then a minus 479.17, and then a minus 479.17, 479.17. Okay. Okay. And then on the right-hand side, we're going to have a plus 15 on the top and then a 5 on the bottom. Okay. And so if we simplify these, these expressions where we have overlaps, we end up with the following. So I'm just going to go erase these because we only just have one overlap here. Okay. And so in this middle here, we're going to have 1500. And on the right side here, we're going to have 20. And so, this assembly is kind of the exact same process that we've followed before, except now, getting the element stiffness matrices and getting the, and applying the loads is, we take a slightly different approach to it. Okay? And of course, everything that we have not filled in here is just going to be still a 0. All right, any questions on this so far before we apply the boundary conditions? Or apply the constraints, I should say. Okay. All right, and so the last step here is that we're going to apply our constraints. Okay. And the only constraint that we have here was that we had a fixed support at x is equal to 0. Okay. Okay. And so what that tells us is that the displacement that coincides with x is equal to 0, which in this case is u1, this is also going to equal to 0. Okay. And so we know what to do at this point. And so now we know that u1 is equal to 0. We're going to knock out that entire first row in the matrix and then just replace it with 1s and 0s. Okay. And so that first row is going to be this one here for our boundary condition. So we're going to knock out this guy. Knock out this guy. We get 1, 0, and then 0. Okay. Okay. And so at this point, we have our linear system is ready. And so all we have to do now is just plug this into MATLAB or plug it into your graphing calculator and then solve for the solution. All right. And so, I went through the liberty of doing this for you, or I should say I did this a year ago when I first wrote these notes. And then we end up with the following solutions. And so we have u1 is equal to 0.0, which makes sense because that's where our, our boundary condition is. u2 is 0.0245 meters. And so that's going to displace about 2.5 centimeters about. And then U3 here is going to be 0.0349 meters. It's about 3.5 centimeters on the far side. Okay. All right. And so if we want to plot this, as a function of x, right? We start here at x is equal to 0, and then let's say that here is the location for x2, and here's the location for x3. Okay, we can see here that u2, we'll say that this is 0.025, and then up here, we can say that we've grown by that much. Right? So this here would be u1, u2, u3. So we can draw kind of a graph that looks like that. Okay. All right, and so that's the finite element method for general finite elements. And so it's still a decent amount of math, but a lot of these things end up kind of simplifying out because a lot of these guys are just constants. Yeah. Back to this page. Oh, okay, great. And so it's a long process, and so I know the theory for finite elements it's not the most exciting in the world, but what I'm hoping to do is to basically help motivate you that underneath the hood of ANSYS, it's not magic, right? It's basically a computer solving a lot of these differential equations, right? And the fact that the theory of finite elements ends up being really dry and mathematical is that these algorithms that we're learning and these methods, they're specifically designed for computers. And what computers are really good at is that they're really good at lots of repetitive, simple calculations, right? that's why, you know, we do all this work to always put our problem into a linear system of equations, because just a computer is just really good at solving those guys, right? And so, hopefully this example here, kind of helps, illustrate, a lot of what's going on under the hood. And, and I picked this example for another reason too. The fact that, we have an area that's changing with space too. Right? And so this would be a problem that would be difficult to do with an exact method, because we have that area function as well. Right? So like we've done a lot of cases where the area is constant, but when the area is kind of changing like this, it really helps to kind of have a computational method to handle this. All right, any final questions before we wrap up for today? Okay, so it's a little bit early, but it's way too short a time to start the next thing, and so I'll leave it here. Okay? Just remember, next Tuesday is going to be our next ANTIS activity, so that's going to be ANTIS activity 3. So you can look forward to that. And then next Thursday is going to be our midterm. Right? So definitely check out the midterm review video that I posted. I think it gives a lot of really good information on the midterm. And if you have any questions with your studying, or you need help with the software or with the homeworks or anything, definitely don't be afraid to reach out to me. Okay? So have a great weekend, everyone. Best of luck studying, and I'll see you guys next week.
See you.
Thanks, guys.
Professor,
Yep. What's up?
I was just wondering, or I had a couple questions about the homework, if you had time.
Yeah, sure. You have a couple minutes. What's up?
So on question, let's see, it's 3A.
Mhm.
For the loads and the applied forces, would we have to do a moment, like M1 would be, or I guess M1 would be 0 because it's fixed, but like M2 would be the force, and then you just put the distance from the force to M2?
No, so the moments would have to be explicit, and so I unfortunately, I didn't give you any examples on this here, but usually, when I want you to apply a moment, it would look something like this in the diagram. So you would have your beam, and I would put kind of like a circly thing like that.
Oh, okay. So if there is no applied moment, we don't assume there's one induced from a force that's
Correct. Yes. Yeah. So any induced moments will already kind of be taken care of in the system. And so, when I have an applied moment, that's like literally someone grabbing it and kind of twisting it like that. So it's not the same thing as a force going down.
Gotcha. Okay.
So for this problem, the solution vector would just be all zeros except for the P from the.
Correct. Yes.
Okay.
Yeah. So the only force you would have is just for the U4Y, which is going to be minus P. Yes.
Got it.
Yeah.
Thank you.
Mm-hmm.
Professor, could you check my matrix, just because like I'm getting it wrong, and I'm just not sure if my matrix is wrong or not.
Okay. Yeah. Let me stop sharing here on my iPad.
Let me